Hello, welcome to class. In today's class, we are going to be looking at electric field 4. We are to calculate how much work is required to carry a charge of 3 times 10 raised to power minus 5 coulomb from a point 50 centimeter from a charge of 2 times 10 raised to power minus 4 coulomb to a point 20 centimeter from it. I will read it again. This question looks a little dicey. Let me read it again so that you get what the question is saying. You need to first understand the question. The question says, how much work is required to carry a charge of 3 times 10 raised to power minus 5 coulomb from a point 50 centimeter from a charge of 2 times 10 raised to power minus 4 coulomb to a point 20 centimeter from it. That is, this charge that we called Q1, that is 3 times 10 raised to power minus 5. We want to carry this charge from point A, that is 50 centimeter from Q2. This charge 3 times 10 raised to power minus 5 coulomb is 50 centimeter from the charge Q2, which is 2 times 10 raised to power minus 4. So we want to carry this charge Q1, that is 3 times 10 raised to power minus 5 coulomb, from point A to point B. That is what the question is telling us to do. If we want to carry this charge Q1, that is 3 times 10 raised to power minus 5 coulomb, from point A to point B, how much work are we going to do? How much work are we going to do? Are we going to do work at all? Yes, we are going to do work in bringing this charge from point A to point B. Don't forget, Q1 is a positive charge, okay, plus 3 times 10 raised to power minus 5 coulomb. If we don't put any sign at the back, it means it is positive. It is plus 3 times 10 raised to power minus 5 coulomb. And Q2 also is a positive charge, plus 2 times 10 raised to power minus 4. Ordinarily, when you have two positive charges, they will repel one another, okay? They will repel one another. So in bringing the charge Q1, that is 3 times 10 raised to power minus 5 coulomb, from point A to point B, we are going to be doing work against the force of repulsion. We are going to be doing work against the force of repulsion, because repulsion will not want the two charges to come together, but we that are bringing it we are going to be doing work against that force of repulsion. And that is why work is going to be done in bringing the charge Q1, which is 3 times 10 raised to power minus 5, from point A to point B. Good. Having understood that, let's look at the formula for work done. Under electric field, what is the formula for work done? This is different from work done under mechanics. This is different from work done under mechanics. Under electric field, work done W can be obtained by Q1 multiplied by electric potential VAB. The charge that we are moving multiplied by the electric potential between the 2 points. Okay, so the work done in moving a charge from point A to point B is given by the product of the charge that we will move from point A to point B and the product of the charge and the potential, electric potential between the 2 points, and the electric potential between the 2 points. That is, at point A there's an electric potential VA. At point B there's also an electric potential VB. So the difference between the electric potential will give us VAB. The difference between the electric potential at A and at B will give us VAB. Please take note of this. It's very, very, very important. This is the secret behind calculating a question like this. When you want to calculate the work done in bringing a charge from point A to point B, it will be equal to the charge that you want to bring, that you want to move, multiplied by the difference in electric potential between the 2 points. The difference in electric potential between the 2 points, that is VAB. Okay, at point A there will be an electric potential at point A as a result of the charge Q2, which is 2 times 10 raised to power minus 4. Also at point B there will be a potential as a VB, a potential VB as a result of the 2 times 10 raised to power minus 4 coulomb that is placed here. Okay, as a result of the Q2 that is placed at this point. Good. All right, now the first thing to do is to calculate our VAB. To calculate our VAB, that is the electric potential. How do we get our electric potential? Our electric potential is KQ all divided by R. KQ all divided by R. Good. KQ all divided by R. Now VAB, which is the potential difference between point A and point B. Let's obtain the potential at A as a result of Q2, which is 2 times 10 raised to power minus 4 coulomb. Okay, that will give us, we'll substitute into this formula. Okay, so our K is 9 times 10 raised to power 9 multiplied by the charge Q2. Okay, the charge Q2, which is 2 times 10 raised to power minus 4. All right, so K, which is 9 times 10 raised to power 9 multiplied by 2 times 10 raised to power minus 4, all divided by 0.5. Where did we get 0.5? Where did we get 0.5? Good. The distance of A from charge Q2, the distance of A from charge Q2 is 50 centimeter. Okay, the distance of point A from charge Q2 is 50 centimeter. Okay, so if we convert 50 centimeter to meter, that will give us 50 divided by 100, and 50 divided by 100 is 0.5. okay, so and that is how we obtained our 0.5 that we have here. That is how we obtained our 0.5 that we have here. Okay, so this gives us an expression, okay, for our potential at A as a result of the 2 times 10 raised to power minus 4 coulomb charge. As a result of the 2 times 10 raised to power minus 4 coulomb charge. Also, let's obtain the potential at B as a result of the 2 times 10 raised to power minus 4 coulomb charge. Okay, so that would be 9, don't forget, KQ all over R. That's the formula for electric potential. So 9 times 10 raised to power 9 times 2 times 10 raised to power minus 4, okay, no, is as a result of the charge Q2. Okay, so 9 times 10 raised to power 9, which is our K, times 2 times 10 raised to power minus 4, all divided by 0.2. Where did we get 0.2? The distance of B to charge Q2, the distance of point B to charge Q2 is 20 centimeter. Is 20 centimeter. Okay, so if we divide 20 centimeter by 100, that will give us 0.2. That will give us 0.2. So that is where we obtained the 0.2 that we have here. That is where we obtained the 0.2 that we have here. Okay, good. So we have obtained the potential at A to be this. We have obtained the potential at A to be this. We have also obtained the potential at B to be this. We have also obtained the potential at B to be this expression. Okay, good. Now, the potential difference VAB. The potential difference VAB. How do we get that? We will simply subtract the potential at B minus the potential at A. Okay, to get the potential difference VAB, is equal to the potential at B minus the potential at A. The potential at B minus the potential at A. The electric potential at B minus the electric potential at A. The electric potential at B minus the electric potential at A. Good. So if we do that, we can factorize 9 times 10 raised to power 9. Okay, that's common. We can also factorize 2 times 10 raised to power minus 4. That's common. So inside the bracket, we'll be left with 1 over 0.2 minus 1 divided by 0.5. Okay, so if we multiply the numerator and the denominator by 10, okay, so that will be 10 divided by 2, that's 5. Also here, if we multiply the numerator by 10 and the denominator by 10, that will give us 10 divided by 5, that is 2. So 5 minus 2, that will give us 3. Okay, so if you press your calculator ordinarily, it will give you 3. If you press your calculator correctly, that will give you 3. So if we multiply 9 times 10 raised to power 9 times 2 times 10 raised to power minus 4 times 3, it will give us 54 times 10 raised to power 5. 54 times 10 raised to power 5. Good. Okay, and what is the unit of electric potential? Volts. The unit of electric potential is volt. The unit of electric potential is volt. Please, very important, don't forget, units are important to us in physics. Good. Now, back to what we are asked to calculate. Actually, we are asked to calculate the work done in bringing Q1, that is 3 times 10 raised to power minus 5, from a point 50 centimeter to a point 20 centimeter from Q2. Okay, good. So in this case, we are going to be using the value of the charge we are moving. We will use the value of the charge we are moving, which is 3 times 10 raised to power minus 5. It is the charge 3 times 10 raised to power minus 5 that we are moving. Okay, so that is the charge that we will use here, which is different from the charge that we used in calculating the electric potential. Okay, the stationary charge, the charge that we are not moving, is the one that we used in calculating the electric potential. Okay, very important, don't make that mistake. It is the charge that is stationary, the charge that we are not moving, the charge that is stationary, the charge that we are not moving, that is the one we will use in calculating our electric potential. But when we want to calculate our work done, okay, the work done on the charge, we will use the charge that we are moving. We will use the charge that we are moving, okay, which is 3 times 10 raised to power minus 5 multiplied by our electric potential, okay, electric potential VAB, okay, electric potential VAB, which we just calculated, and that is 54 times 10 raised to power 5. If we multiply this correctly, it will give us 162 joules. If we multiply it correctly, it will give us 162 joules. Okay, so the unit of work done is joules. It's also the same under mechanics. The unit of work done is joules. Thank you for your listening attention. Hope to see you in the next class. Bye.